Alright, so next part we are going to discuss about the important notation for integration. So as we know that there are the three type of integration we are going to do. That the first one you are the single integration or line integration where we generally use in evaluating the line integration. And second we are going to see here the second double integration, which is generally used in your integrating the area. And third one is your the triple integration, which is generally used in the volume integration. So I'll do that. There's some basic notation. First one for your single integration. Okay, so this is the sign for the single integration. Okay, so in this the single integration we need to use the two types of method. That is, the first one is your the basic method or the basic approach, where we generally use to direct integrate uh, dx, and this is the dy, just like this. Okay, and second one is your, at the second one, this is the second one, in which we have a polar form. Okay, so this is the polar form. Thus the polar form means you are going to evaluate the line in your the circle integration. So this is the like a ring type and structure. So you can you have to uh, remove this the part where the x is equal to r cos theta and y equal to r sin theta. This need to be put in your the equation which you need to integrate. Okay, so this is the x and y. Alright, so what is the dx? You need to differentiate for the derivative element. So that's why this is the dr equal to, r is the constant because we have already fixed with that your ring type of structure. So that's why this is the r. So r, and this is the cos theta, and this is the d theta. And for the y also we can write here, this is the dy equal to r, this is the sine theta into d theta. Okay, so you need to replace this is the dy and dx while using this method. Okay, alright, so r is the constant in this part, and the second one is your double integration. This is the double integration in which we have the two part. The first one is that the first one. Okay, so the first one is the basic method, and second method we are going to use here polar form. Okay, so this is the same thing which we have done in the previous one for. So that is your okay, so this is your first method is basic method. Okay, so in this the basic method you have to integrate directly dx and dy, means the area. So this is the surface area we need to integrate by using this method. Okay, this is the simple analysis. And my second method is your the polar form. Okay, so this is the polar form in which we will have here the disk, and here the radius in r will change. Like us, you just have to integrate the lot of the ring which can form this is the disk like this. Okay, so this is types of the polar form. I think this is the r is variable, so you can say this is the variable, and here theta is also variable. Here you need to remember this is the ring and this is the disk. Okay, so here by the way we need to remove this is the x equal to r cos theta and y equal to r sin theta, and for this the part dx and dy need to be removed. Y r dr d theta. Okay, so need to remove this dx and dy will be removed by r d theta and dr. Okay, so this is the second method for your the surface integration. Next part we are going to see here volume integration. Okay, so this is the volume integration. Okay, so this is the third one, is your volume integration. The sign is look like as here. This is the volume integration here, or concept triple integration. So here we are going to see this is the three types, or can say four types of condition. Okay, so first one, I have to make some line, should be more clear for you. So this is the second, and this is your third, and next one is your fourth. Alright, so first method is the same which we have done in the previous one. So this is the basic method, the basic analogy. So this is the basic method. Basic method, you need to integrate directly dx, dy and dz. Okay, so with respect to that, you need to integrate here the volume dx and dy and dz. Okay, next part is your the projection method. Here we are going to use the projection method. And this is the projection method. Just you have to do that the projection, and the projection will be formed in your the xy plane or yz plane. Means this is the simple 2D plane. You need to convert your the 3D object into the 2D object. That is the projection. Okay, so after when you will convert that part, you need to integrate the same way which we have done in the second type integration, double integration. Like so, that's the method will be applicable for all the types of your the 2D planes. So that's why we have to use the projection method, in which we have to do firstly we need to integrate with respect to z. It means the 3D object is like that. Okay, so this is the z axis, this is the x axis, and this is the y axis. So we need to integrate with this the z axis. If the object look like that, which will have the projection will be formed in your the xy plane, then you have to in the dz plane. Okay, so this is the dz plane. After that, you will be in 2D plane. Okay, you will be in a 2D plane. Okay, so that is the condition. Now we need to do the next method analogy here. A method for we need to go 2D plane. Okay, next part is your two types of the two object in your the 3D plane, like cylindrical object and spherical object. Okay, so this is the cylindrical object, this is the cylindrical type structure. Okay, if we will have that the cylindrical type structure, what you need to do here, this is the projection method will be applicable for projection method. You can use the projection method to evaluate the cylindrical types of body. And second method is your the cylindrical coordinate system. Okay, so cylindrical coordinate system. You can use the either your the projection method or the cylindrical coordinate system, any which you can any one of them you can use that. So that is you need to remove here in the cylindrical coordinate system r x equal to r cos phi, y equal to r sin phi, and here the z equal to z. Okay, so this is the 3D body, and here you need to remember this is the phi angle, in your the xy plane. So I will say this is the phi angle and this is the z. Okay, so we need to go for that. And if you will have the spherical coordinate system, spherical system types of the body, then you need to go for only spherical. spher- spherical coordinate system, in which we need to remove the x, y, r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. All right, and here we need to change dx, dy, and dz, y r square sine theta d theta dr and d phi. So if you will see here what is the theta and phi and r, you can see this type of the spherical body here, and the theta, this is the phi angle which we have seen in your the spherical body is the same as here also. So this is the phi angle, and this is the theta angle, this is the theta angle, this is the direction, or you can say this is the theta angle, this is the theta angle. And what is the r is the radius. Okay, so r is the radius. All right, so this types of analogy we need to remember, and here you can use the variety of method, but in a spherical coordinate, in a spherical body, you need to go for only spherical coordinate system. That will be easy for you. Otherwise, if you will go by using some basic method like basic or projection method, that will be more complicated in comparison to this type of the spherical coordinate system. Okay, so this is the general type of the structure you can use any of them. And one more thing I forgot, that this is the spherical coordinate, it's a cylindrical coordinate system. We need to write here the dx, dy, and dz also are dr, d theta, and dz. You need to remove this part also. Okay, so this is the thing we need to see here. This is the, can say, the proper notation for the integration, the basic integration you can use. Okay, so we we have to move the next part.